A buck regulator is a DC-DC converter which converts a higher voltage potential to a lower voltage potential. It uses a switching element to ensure steady DC output of required voltage. I am Reshma, and today we will discuss the operation of a buck regulator. In this topic today, we will learn more on diode average current, diode RMS current, diode peak current of buck converter in continuous conduction mode. When the switch is turned on, the diode is reverse biased and it does not conduct. Hence, the current is 0 amps for the diode during this time. However, when the switch is turned off, the diode is forward biased. The current flowing in the inductor is same as the current flowing in the diode. Hence, the diode current when the switch is turned off is the falling current of the inductor. Hence, diode current is equal to the falling current of the inductor IL2 of t. From our earlier videos, we saw that the falling current of the inductor is given as shown here. As the falling current is equal to the diode current, we can say that this current is equal to the diode current. Hence, in one cycle, we can say that diode current is 0 amps during switch turn on, and it is only present when the switch is turned off. Now that we have established the diode current equation, let us now derive the average diode current. Average diode current is the integration of diode current over one cycle. Let us now split the terms into on and off times. It can be simplified as shown here. While deriving the average inductor current equation, we saw that integration of falling current of the inductor is equal to T into 1 minus T into I1 plus I2 divided by 2. Hence, we can substitute this value in the average diode current equation. The resulting equation is shown here. We can now substitute the integration of falling current of the inductor in average diode current equation. Now we get this equation. In this equation, T and T gets cancelled, and the diode average current is given as 1 minus T into I1 plus I2 divided by 2. We can see that diode average current is dependent on the duty cycle and the ripple current. From our previous equations, we know that I1 and I2 can be represented in terms of average inductor current and ripple current. We know the average diode current equation that we derived in the last slide. Let us now substitute the value of I1 and I2 in the average diode current equation. We can cancel out the common terms. On simplifying, we get diode average current equal to 1 minus T into inductor average current. Let us now look at the RMS diode current. RMS current is given as square root of 1 by T into integral 0 to T diode current square of T into dt. Now, we saw that diode current is present only when the switch is off and it is 0 amps when the switch is turned on. Square of diode current can be represented as shown here. Let us now split the terms with on and off times. Diode current during switch on time is equal to 0 amps. Hence, we can consider only during the off time of the switch. In our previous videos, we saw that falling current of the inductor is equal to the equation as shown here. As diode current is equal to the inductor falling current during off time of the switch, this is also equal to the diode current. We have also previously seen that squaring of the falling current of the inductor and integrating it gives 1 by 3 into T into 1 minus T into I1 square plus I2 square plus I1 I2. We can now substitute this value in the above equation. After substituting, we get 1 by 3 into T into 1 minus D into I1 square plus I2 square plus I1 I2. We can now write the square of integration of falling current of the inductor in RMS diode current equation. After substituting, we get this equation. Here, T and T gets cancelled and we obtain the equation as shown here. Thus, we can write the RMS current equation as square root of 1 minus T into I1 square plus I2 square plus I1 I2 divided by 3. From our previous equations, we know that I1 and I2 can be represented in terms of average inductor current and ripple current. We know the RMS diode current equation that we derived in the last slide. Let us now substitute the value of I1 and I2 in RMS diode current equation. We get the equation as shown below. We can use a plus b whole square, a minus b whole square and a plus b into a minus b formulas for simplification. Here, few terms gets cancelled out. On simplification, we get this value as shown here. If we take 1 by 3 inside the bracket, we get the equation as represented below. Thus, RMS switch current value can be written in terms of average inductor current and ripple current as shown here. Let us now look at the diode peak current equation. We can see here that I2 is the peak current. This is nothing but the inductor peak current. Thus, diode peak current can be written as inductor peak current, which is also equal to inductor average current plus delta I by 2. To conclude, we can write diode average current is equal to 1 minus T into I1 plus I2 divided by 2. Diode average current is also equal to 1 minus T into inductor average current. Diode RMS equation is equal to square root of 1 minus T into I1 square plus I2 square plus I1 I2 divided by 3. Diode RMS current is also equal to square root of 1 minus T into inductor average current square plus delta I square by 12. Diode peak current is also equal to inductor average current plus delta I by 2. In this video, we saw diode current equations. We will learn more in our subsequent videos. Until then, let's keep exploring and learning. Thank you.